Hi, welcome to part 4 and last of this series on controversies in physics. If you haven't seen all 3 of my previous videos, since they are intended to be viewed in a specific order, I would strongly suggest that you start at the beginning. In this video, we will be looking at just a few of the paradoxes and incongruities which drove me to investigate the following foundation. This one has to be physics' mother of all blunders. This misconception is so inconceivable that it can only go one of 2 ways. Or you flat out put on blinders and refuse to even think about it, or you can no longer trust any of the physics you were ever taught in school. This is Benoit Launier, the black sheep of physics. So without further ado, hang on. This one is downright disturbing. Welcome back. The following 2 excerpts describe Thomas Young's perception of energy as well as the mathematical forethought he formulated to evaluate it. Excerpt number 1. In mechanics, Young established many important concepts in the course of lectures published in 1807. He was the first to use the term energy for the product of the mass of a body with the square of its velocity and the expression labor expended, that is, work done, for the product of the force exerted on a body with the distance through which it moved. He also stated that these 2 products are proportional to each other. This excerpt was extracted from the book The Biographical Dictionary of Scientists by R. Potter and M. Ogilvy. Excerpt number 2. In the lecture on collision, Young goes further and defines this energy as the mass of a body multiplied by the square of its velocity, E equal mv squared. Thomas Young wrote, "The term energy may be applied with great propriety to the product of the mass or weight of a body into the square of the number expressing its velocity." This excerpt was extracted from the book The Man Who Knew Everything by Andrew Robinson. First of all, most people, including many scientists, like Thomas Young, confuse mass and weight. A body's mass depends on the amount of matter the body is made of. This quantity does not change regardless of the location where a body may be. A body's weight, on the other hand, depends on the mutual gravitational attraction it has towards a celestial body. A body's weight changes with location. A body which has a mass of 1 kilogram only weighs 1 kilogram at sea level on Earth. Everywhere else, the body's mass remains the same, while its weight depends on its gravitational submission. So, what is energy? Energy is defined as a scalar quantity, that is, an amount of, a body or system is said to possess, which gives it the capacity to cause change upon another body or system. According to Thomas Young's conceptual interpretation, which became our present-day classical institution, energy is evaluated as a corollary to the work done by a force applied upon a body per the distance the body is displaced during which time the force acts upon it. In order to ensure our analysis will not be deceived by external influences, we need to imagine a region of empty space so far removed from all gravitational fields and other constraints that we would have before us the perfect resistance-free environment. In such a resistance-free environment, when a constant force impresses linearly upon a body, the body is subjected to a constant acceleration, thus to a linear change in velocity in the course of time. This is the second law of motion. This translates to an exponential change in the distance the body covers during that time. Because, in the course of time, a constant force requires a constant supply of energy to maintain that force constant, Now, let me repeat this to make it very clear. Because, in the course of time, a constant force requires a constant supply of energy to maintain that force constant. This means that the amount of kinetic energy the body gained or lost during which time the force acted upon it is indisputably linearly proportional to the body's velocity gained or lost as well. In other words, Young's energy is incongruous to the laws of motion and to the conservation of energy law, because a uniform expenditure of energy cannot produce an exponential increase or decrease in energy in return. This is the first clue suggesting that there is a problem with Young's energy institution, force per displacement. Now, let's go a little further and look at another issue pertaining to our classical energy principle. In that same region of empty space, at spacetime S1 T1, let's assume two bodies, A and B, in motion in a direct linear collision course one to the other. We will also make the mass of body B to be twice that of body A. When the two bodies collide, they both undergo a deceleration, thus a loss of momentum relative to one another. On the other hand, from the perspective of each body, since each body was originally at rest to itself, each body undergoes an acceleration relative to its original at-rest state before the impact. Thus, each body undergoes a gain in momentum relative to its original state. If we further assume an idealized elastic collision, there will be a momentary deformation, compression, of at least one or of both bodies during the impact, until at spacetime S2T2, the two bodies reach the at-rest state one to the other. Then, at spacetime S3T3, the elastic recovery of the potential energy stored into the deformations of the bodies will drive even more negative momentum upon each body in reference to one another, and more positive momentum in reference to each body's original at-rest state before the impact. This means that, under an impact collision, our assumption that one body loses energy while the other body is transferred that energy is deceiving. This assumption nearly always pertains to a perspective that comes from an observer, which can be another body or system, which does not take part in the event. This reveals a second clue that we also have a problem in the manner in which we have been taught to evaluate an energy exchange. Let's pursue our investigation a little further yet. Because there is only one force which reciprocally develops between body A and body B during the intervals of the impact and recovery cycles of the confrontation, this means that the magnitude of that force and the time for which it acted upon each body were necessarily the same. This is the third law of motion. Since body A has a lesser mass than that of body B, its differential velocity during the intervals of the confrontation was obviously greater than that of body B. This also means that the differential distance body A covered during which time the force acted upon it was necessarily also greater than that of body B. This is a third clue which further confirms that Young's energy, force per displacement, is in disagreement with the laws of motion and the conservation of energy law. Now, let's look at our classical kinetic energy. Classically, kinetic energy is defined as the energy a body acquires in virtue of being in motion. Since a body's motion can only be referenced to another body or system, this means that a body can possess as many values of kinetic energy as it exhibits velocities of motion to other bodies or systems. Furthermore, because the amount of energy a body can exchange with another body or system can only be evaluated as a corollary to the change it can impose upon the other body or system or upon itself in consequence of the confrontation, the kinetic energy of a body necessarily also depends on the reciprocity caused by the other body or system's mass. But then, Young's kinetic energy 1/2 mv squared, does not take into consideration the reciprocity caused by the other body or system's mass. This further reveals that our classical definition of a body's kinetic energy, even if its equation were true, would still be inappropriate. And this is merely the tip of the iceberg, because Einstein's energy, E, since it rests upon Young's misconceived foundation, force per displacement, cannot be equal to mc squared either. When I confront other physicists with Young's energy misconception, many of them respond, "Everybody knows this." Well, how completely irrational is that? If everyone knows that it's wrong, then why do we continue using it, and why has it not been corrected yet? The reason why Thomas Young chose force per distance instead of force per time is that he wanted to separate energy from momentum. But in order for a body to acquire kinetic energy, it necessarily possesses momentum as well. The two are inseparable. Yes, there is a distinction between energy and momentum, but the distinction lies in the reciprocity caused by the other body or system's mass. Even then, stripping away all external hindrances, one is indisputably a linear derivative of the other, definitely not exponential. I am well aware that disagreeing with the establishment will provoke a lot of animosity and desperate attempts to discredit my work. Just imagine the resistance against having to rewrite every physics book in the world. And this is without even considering all that must be discarded only to start all over again. However, when conflicting or irrational results show up in empirical investigations, the sources of the disagreements must be attributed to the right reasons, which, in most cases, are shortcomings in the theories themselves. Some physicists, especially teachers, decree that I am uneducated because my theories and equations are not what they have learned and teach. They are so academically indoctrinated that they simply don't get it. They scan the pages of my book and see equations they don't recognize, and without investigating any further, consider them to be wrong. The whole point of my treatise is to demonstrate that some of our classical theories and equations are flawed. So naturally, my theories and equations are different than what is being thought. I made this series of videos to give you just an overview of the readjustments necessary in order to rationalize physics under a single set of universal laws. All of the misconceptions stated in these videos, as well as many others, are examined much more extensively in my book, The Universal Physics Theory, 5th edition. Mind you, due to the extent of the ramifications, in no way am I able to correct all of the possible offsprings deriving from these readjustments. Thank you for watching my series on controversies in physics. I hope it was informative. And if you liked it, please share it with others.